All right, hello again, aficionados. So I'm on a roll here. This is going to be video number 3 today, and this is going to be, without question, the most important one because we are going to tackle something that has eluded me for a while now. We're going to talk about STEM-EELS today. Okay, I have the perfect test sample for this. It's got 4 elements in it that have very nicely separated core loss edges, so there really isn't better test sample to use for doing this today. So I'm going to give you a soup to nuts tutorial here, hopefully, about how to do this, and let's have an adventure. So if you saw the video on coma-free alignment, it's the same sample we have here. So it is a silicon substrate, and it's got a thin silicon germanium epi-layer on it. Actually, let me pull up. Okay, this is a high-res image of the structure. So silicon substrate, this dark band right here, this is silicon germanium, and it's got silicon on top of it. There is an oxide on top of it, which we can't really see very well in the high-res image. And then it's got amorphous carbon. Okay, so it's got 4 elements, right? So we've got carbon, or sorry, if we go in terms of the core loss edges order, we have silicon, then carbon, then oxygen, then germanium. Okay, and you'll see what I mean by the order of the core loss edges when we get to that. Okay, so anyways, we're going to map over a scale very similar to what we see here. Okay, so hopefully we can analytically resolve all of those different regions. Okay, so the carbon overlayer, the oxide, the top silicon, the underlying silicon germanium, and then the silicon substrate underneath. Okay, all right, so before we get to the good stuff, meaning the actual doing of the eels, we need to, I'll push you centric focus here. We need to actually tune the eels spectrometer. Okay, so I'm just trying to set the eccentric focus here. Yeah, it's right about there. Okay. And I'm going to go ahead and put in an objective aperture here. Of course, when we get to doing the STEM-EELS, it's going to be completely different, but as you're going to see here, this is a necessary prerequisite to this. Okay. All right, we'll turn diffraction off. Okay, so we're going to do a couple things here. So the first thing we're going to do is we're actually going to tune the GIF in what's called FTEM mode. Okay, and so I'll talk about the 2 operating modes of the GIF here in a minute. So and we want to tune it with a parallel incident beam where we're over vacuum. So we're not actually over vacuum right now. We'll get to that in a second. But what you want, there should be a panel called filter, and then there's a button in here called FTEM. Okay, so when you do this, what happens is you change the projection system of the microscope. So basically everything that is below the objective lens. Okay, so your projection, the lenses in your projection system. So if we look here, right, basically that means everything down here, diffraction, intermediate, projector 1, like these all end up changing when we switch into FTEM mode. Okay, so I'm going to go ahead and push here. Actually, I'm going to pull up so you can see this system status, and then push FTEM. Okay, so you can see what happened, right? These all went completely wonky here. Let me go back here just so we can watch. Okay, so it did change condenser 2 and condenser 3. It didn't change the spot number, but the important part is the projection system. So let me go ahead and push FTEM here. So it runs normalization. All right, let me go back to, I'm going to set this at SA 40,000. And then I'm going to switch my blue cam to what's called high resolution mode. Okay, center my beam. And then I'm going to spread my beam out. So now you may have on your flue cam an annotation here for the GIF entrance aperture size. So I know on my system, this actually corresponds to the maximum width of the viewable area of the GIF. So you can see that we're, illuminating well in excess of that, okay? Let's see, I thought I was going to be at 40,000. Let me go back one click here. Okay, so you can actually see when you look in here, you can actually see a really magged out image of the sample. Okay, so when we actually put this onto the GIF, you're actually going to see an image here. So I'm going to switch the screen input now to the GIF monitor. So give me a second here. I'm going to walk back over to the room. All right, so it looks like it's extending the desktop. So let me see. I can't get it to mirror the displays here. Display settings. Identify. Okay. So what's going on here? Okay, so I think we're okay now. Here, let me stop the share and then start the share again just to make sure. Okay, there we go. All right, so there's our digital micrograph. Okay, so over here you can see that we have FTEM mode activated. So basically in FTEM mode, whatever you have on your viewing screen, this is what you're going to see an image of when we start imaging. Okay, so whether that's an image or a diffraction pattern doesn't matter. This is what's called FTEM mode. You're projecting an image of whatever is on the screen onto the GIF. Okay, if we're in EELS mode, what we're doing is we're projecting an EELS spectrum onto the GIF instead. Okay, so whether we have an image or a diffraction pattern, it doesn't really matter here. That's what we're going to be putting onto the GIF. So what we want to be in right now is FTEM mode. Okay, so if we come over here, the technique manager, and we can put this on FTEM map for now. Okay, and we're going to start in HDR mode and click view. Ooh, well, that's pretty nasty. Oh, I don't have the screen in, or I don't have the, let me take the screen out of the way. There we go. Okay. All right. So I want to move the sample out of the way. So we just have open area. And then I'm going to come over here to where it says tune GIF. And I'm going to push tune GIF. It's going to give you a message here. Make sure you're only in vacuum. And then this is going to run through its little automated routine. I don't like that. Lines it's given me. I don't know if that means we need a new gain reference. Maybe we do. Yeah, I'm thinking we need to take some new reference images here. So okay, I think we need to do that. All right, saying system tune successful. So this looks okay, but then if I put the screen in, I'm seeing this. I shouldn't be seeing this. So that's either an issue with well, it's probably an issue with the reference images. Well, that's not good. All right, what are we gonna do here? What we're gonna do is take some new reference images. So I'm gonna come back here. I'm closing the column valves. It's not a bad idea to do this anyway. I'm gonna switch to power user, camera, and we're gonna prepare a dark reference. So while this is doing its thing here, so again, the four elements of interest are, and again, they're by order of edge and or core loss edge energy are silicon, carbon, oxygen, and germanium. Okay, so silicon L23, which has the lowest energy edge, it's around 100 electron volts. Then you have the carbon K edge, which is around 284 volts, electron volts. And then you have the oxygen K edge, which is, I believe, around 550, somewhere in that vicinity. I got my little EELS cheat sheet right here. So let me take a look here. So yeah, oxygen is 532 according to this diagram. And then the germanium L23 edge, which is at around 1217 electron volts. So basically the entire energy window that we need to capture all of those core loss edges. So the energy differential is 1100 electron volts. So we're probably going to need, yeah, 1500 electron volts. I'm thinking to get all four of those edges in there, which is perfectly fine. We can absolutely do that. So we'll see how we can change the energy window by modulating the what's called dispersion. First, we got to get rid of these nasty lines here. So we're going to just collect some new reference images. Those are actually all core loss edges that are very easy to detect too, which is nice. So with the silicon, it has a K core loss edge, which is much higher energy. That's about 1800, I think, electron volts. Again, according to the 1840. So it's inelastic cross section is much smaller than the L23 edge. So, okay, dark images have been successfully acquired. So let's see what we get now when we look at this. Do the lines go away? Yes, they do. Okay, so let me open the column valves. Okay, let me pull the screen out of the way. Now you can also just click on the screen here, and that will also remove it. All right, and so the gain reference looks fine, but we might as well, let's take a new gain reference. Okay, so let's go prepare gain reference. So again, make sure you're in vacuum, you have even illumination. And it's asking for the average intensity to be between 250 and 351. So we have to spread the beam out a little more till we're at 3. There we go. Okay, and we'll click done. Apply to 200 kilovolts. Yes. So the gain reference and the dark reference, this applies equally whether you're doing FTEM or EELS, okay? So that uses reference images for both of those. So that's why it's important to have, good quality references. And then once this is done, we're gonna go ahead and, we'll retune the GIF. The sample I've had in here has been sitting in here for several hours, so it's gonna be nice and stable. Specimen stability is really pretty critical when you're doing, EELS mapping, especially, close to the atomic level. As we're going to see here with EELS, especially because we have a detector on this, which is not direct detect. So, we have to use a sufficiently long exposure time to make sure we have decent signal to noise in the spectra. So what we're going to find is we're usually going to be using pixel times, of around a millisecond, probably when we're, doing the map collection. So. All right, this is it, last mode, mode 4. Okay, let's take a look. So quick note here, when when you're doing the imaging here, HDR, this is high dynamic range, this is low dose. With HDR, what it's doing is it's summing frames, and each frame is acquired over 10.6 milliseconds. Okay, so if let's say I set this, say I quadruple this, okay? What I'm doing is I'm summing 4 frames here, okay? I'm not changing the exposure time. I'm just summing 4 frames now, each with exposure time of 10.6 milliseconds, okay?
So in this case, now I'm summing 8 frames. Okay, I mean, obviously it's just a beam on here, but that's the difference, okay? If I was in low dose mode, I'd actually would be integrating over this time and not summing frames, okay? So that's the difference. To quickly go back to the minimum, I can just type in 0, and that will put me back to 10.6 milliseconds. All right, so let's go ahead. We're going to tune the GIF now again. And we'll make sure that we're not seeing any of those. Yeah, so those lines are gone, so we should be good to go now. All right, now it's doing the mask correction, which is the last thing. I should say mask correction. All right, and we're good. All right. All right, so let me pull the sample back in because now we're going to do something else here while we're in FTEM mode, and that is we are going to figure out how thick our sample is, okay? So we can do this right now. We can save ourselves a lot of trouble by doing a thickness map in FTEM mode. And you can also do this in STEM mode, but this is really quick to do in FTEM mode, okay? Without having to do this when we get into STEM mode, okay? So again, we're in the FTEM mapping technique here, okay? And now we want to come down here to set up and acquire thickness map, okay? And so here we can specify the width of the energy selecting slit. So here really quickly here. Okay, so you can put in the slit here. So the slit, so now we have a 20 EV slit centered around the ZLP. Okay, so I can make this smaller and watch what happens here. Okay, so now, right, we're starting to see the edges of the slit. So yeah, so really around 5 EV, we're not seeing the edges here. So we could use that here to do this. But now this is a 0 loss filtered image. Okay, so if I take out the slit, okay, that is, with inelastic contributions. And then that is with only elastic contributions. Okay, so the fact that we're not seeing much of a difference tells me that the sample is probably really thin. Okay, but anyways, all right, so let's do 5 EV slit width, and we'll set the binning at 2, and yeah, we'll use 1 second exposure here, and we'll click capture, and this will go ahead and do its thing. Okay, so it's doing cross correlation here. Don't need to worry about this. Okay, so now it's giving us mean free path, so relative thickness, and it's going from 0 to 3, but we're down here in the blue. So if we want to change this, you do Control D. Okay, if you click Auto Survey, okay, there we go. All right, so basically the thickest part of the film is around 0.6 mean free path. And then as we, obviously as we get into vacuum, right, our mean free path is going to be 0. So, as and we can mouse around in here so we can see right down here, it's telling us what the mean free path is, okay? So this is the carbon right here, okay? So in the carbon, our mean free path is, around 0.25-ish, 0.3. And then in here, it's a little bit more, around 0.3, 0.4. But this is plenty thin to do STEM-EELS mapping on, okay? And to be clear, we can get a better quality map than this by, exposing for a longer time. So let's go ahead and do that. Okay, so it blanked the beam. I had it set to do that. So let's go ahead and collect another map here. Let's do, let's do 5 seconds. So it should correct for the drift while it's doing this. All right, let's do the same thing. Okay, yeah, so a little better, but basically same result, right? So obviously the longer you count, the better your signal to noise is going to be. So yeah, down here in vacuum, we get, mean free path, which is, basically 0. So again, it's mean free path in terms of plasmon scattering events, okay? So plasmons, those are your most common inelastic scattering event, okay? What we're concerned about when we do EELS mapping, though, usually, right, is we're interested in mapping core loss edges. So those are different than the plasmon. So we're going to see this in a second here, okay? Anyways, so we verified that we got a good enough sample to do EELS on, okay? All right, so what I'm going to do now, okay, beam's blanked. I'm going to put the screen in. And I'm going to switch the input back to the microscope side. All right, and so we're going to switch out of FTEM mode. Okay, I'm going to unblank the beam. Have this set for my R3 button here. All right, and so now we're going to set the instrument up in STEM mode. Okay, so because we have the monochromator on here, we need to change our monochromator setting. So where are you? Okay, so we want to go positive focus here in STEM. Had a little bit of a drift there, but that's okay. I'm gonna set it up now. And there we go. Okay. And we're gonna find our apertures panel, take out our objective. So, a quick note here, when you're in F10 mode, your objective aperture is what defines your collection angle, okay? And of course, because we were doing, zero loss filtering, we don't need a very high collection angle for that. So, all right. And now at this point, we are ready to head into STEM mode. So we're going to find the STEM tab, hit the STEM button, zero out the scan rotation. Okay, so right now we're at spot 9, which is giving us around 40 picoamps. And we've got a semi-angle of convergence for 22 millirating. That's fine because we're going to be doing this at or near atomic resolution. So this is a reasonable condition. You can do STEM-EELS in microprobe mode as well, and I have done that to good effect. So if we weren't doing something near the atomic scale, we could do that. Okay, but since we are, it makes more sense to use nanoprobe, so we'll leave it there. Okay. Now in terms of the spot number, we really can't because of if we had a direct detect GIF, we could do this, but we don't. Okay, so we're gonna need more current than this, or else, our EELS spectra are just gonna be noise. Okay, so I probably wouldn't do. Now again, this is a matter of opinion. Okay, my opinion is, at least a couple hundred picoamps here. I personally like to kind of take like what I call the flash fry approach when I do EELS, meaning like one pass with as much current as possible. So if we wanted to do that, maybe around 400 picoamps. So if we put it at spot 6, yeah, that's about 300. If we go to spot 5, that's a little too high. Yeah, so let's go to spot 6 and we'll leave it there. Okay. All right. So we need to, align in STEM mode. Okay. So we're in acquisition here. Let's click HADIF. Right click and center beam, and then freeze. Okay, we want to be at high mag here, and then we can turn diffraction off. Okay, take out the STEM detector, and here we go. All right, so there's our caustic spot. It looks like it's pretty well centered, so we can turn on. And again, if we want to reset everything here with the auto tuning, we can open up auto tuning, click reset. Push eccentric focus, even though we didn't need to, it was already at its default setting. Okay, so sometimes, yeah, so this helps. If you switch this to temperature, you can see so we're a little bit off with the beam tilt. Okay, so go to beam tilt. And that looks a lot better. Switch back to grayscale. And use your beam shift. There we go. And of course, we're at basically the highest possible. Is that the highest possible? We can go one more, but yeah, basically the highest possible SA mode with diffraction off. And then we'll turn diffraction on. So we see the direct disk again. Right, it looks nice and centered on the screen. I'll go ahead and bump up the camera length a couple clicks here just to make our alignment easier. Okay, and then find direct alignments, diffraction alignment. Make sure this is nice and centered. Find apertures and then put in the 150. Okay, that's clearly not centered. Okay, it looks good. All right, so now we need to get something under the beam. Okay, so I know that the sample was down here. So if I push up with the joystick, I should run into the electron beam platinum. First of all, oh, there we go. There it is. Okay, so we want to focus with the Z. So I'm going to use my Z axis here to get in the ballpark until I get as close to blow up as I can. Switch this to piezo move Z. Whoa, that was really coarse. Okay. All right. And now we can check A2, A1, course A1 and course B2. So, I mean, it looks like we're pretty reasonable here with, there's probably both of these actually. So let's do B2 first. We'll turn on probe B2. All right, so we got a little bit there. ATB2. All right, that looks good, reasonable. And then ATA1, make sure that's set on bit 0, which it is. Okay, right about there. And of course, our final tweaking we're going to have to do actually looking at the image. So we'll put the 70 back in. Okay, make sure that's nice and precisely centered. Turn off high resolution mode. Go back down to 115 for the camera length. And we'll start imaging. All right, so we need to adjust our detector settings here. Pull the gain down. Pull the offset up. Pull the gain back down. All right. So clearly we have some astigmatism here. So we can, hand this over to auto stem here, or OptiStem, I should say, to just do this really quickly. Okay. Now, because we're not, I mean, you can do atomic resolution STEM-EELS. Okay, that is absolutely possible to do. We should be good to go though, just by doing, C1, A1 auto tuning and just kind of leaving it at that. That extra few picometers of resolution, for doing STEM-EELS is really not going to make or break us, at least in my opinion. So just to kind of save time. So we can pause, open up Sherpa, do tune C1, A1. All right, let's see what we got here. Okay, and yeah, that worked perfectly fine. Okay, so now, all right, now we can see more clearly the epi-layers I was telling you about. So we want to make sure that our zone axis alignment is, good here. Try that again. There we go. All right, so let me pull up the flu cam. All right, that's embedded. So how do I do this? Acquisition, that's right. Okay. So again, we only need, like, the area we're going to ultimately do eels on is going to be really small. Okay, it's only going to be, like, well, let's see, that's 50 nanometers. So just to give you an idea, it's probably going to be something like this. Okay, so if we actually look at the object properties, so that's like 50 by 20 nanometers. Okay, so not a big area. So we only need good zone axis alignment here. Okay, so what we kind of see here is as it's scanning along. Okay, so we're definitely, like, as it's scanning here, it's getting closer. Yeah, so we're definitely off more, toward the surface. So we got a little work to do here. So let's mag out. So we got to do minus alpha here. Okay, that looks a little better. All right, that looks a lot better. Especially if we're doing atomic res, you know, having good zone axis alignment becomes really important. All right, that looks pretty good. Okay. And so again, we can see the structure here pretty obviously, right? So this is silicon, this is silicon germanium, this is silicon, then you can clearly see the oxide, and then you can clearly see the carbon on top of it. So this is this is perfect here, okay? We're gonna again fine tune the picture here once we actually get into all right, so now this is important here. We want to make sure we have a good place to park the beam so we're not, you know, obliterating anything. So I'm going to park it right there and stop. And I'm going to, well, actually, you know what I'm going to do here? Let me center the beam and we'll center it over the carbon for now. Okay. Now this is another thing that's important here is when we go to do eels, we got to check the D-scan and activate this, okay? This is going to ensure that as the, and again, at this scale we're working on, this isn't like really critical. If this is like a wider scale, like micro scale, this becomes more important, but this ensures that we don't see shifting of the eel spectrum along the energy axis as the beam is scanned, okay? So we want to check this. And I'm going to freeze this and then blank, so we're not pasting the sample. And then I am now going to switch the microscope. Again, find the filter panel and click FTEM, okay? So now we have a diffraction pattern on the screen, okay? And then I'm going to increase my camera length. So now it said 115 in regular mode, and now it says 240 in FTEM mode. I'm going to increase this to 400 because I know that this is going to give me a more appropriate collection angle for my eel spectrometer, okay? All right, so I'm going to go ahead and swap the monitors back here to the Gatan PC, and that should be the last time that I need to do that. Excuse me as I grab a drink here. All right. So we still have the system in FTEM mode, which is fine. We do want to switch techniques here though. So go to the technique manager and we're going to switch to STEM-SI or spectrum imaging. Click on view and we can start by doing this STEM alignment panel here. Okay, so we're going to click start. So now we have to retract the screen. So it's going to do this automatically. Okay, because the beam is blanked, all right? So we can unblank the beam. So actually we can do this right here, okay? Okay, there we go. So there's our beam. We're not oversaturating it right now. So now right here, I can click auto center disk. And now if you have calibrated your GIF for the different camera length settings, you can actually now measure your angles here. Okay, so we come here to click alpha. Okay, we can increase this to 22. It's a little bit off from what it's reading, but it's close enough. We can switch the aperture. Right now we have imaging, which is basically outside the area, and we want to switch this to high signal to noise. We come here on display. And we really can't see much here. Let me see if I move this down. Okay, there we go. So we can actually kind of see something there. There we go. Okay, so that's the edge. That's the EELS spectrometer entrance aperture edge. Okay. So this is giving us a collection angle of about 61 millirads. Okay, so we want something that's usually about 2 to 3 times what our semi-angle of collection is for the incident beam. Okay, so we're right on target here. Okay, so we can stop this. Okay, and then now come back here to microscope, and we can click EELS. Okay, so let's start by scanning or starting the scan. So now there's a little input box. You can't see this, but I have to change the scan input to GIF. And then I can click view up here. And there we go. Okay. And then over here, you don't have contrast and brightness. You just have auto gain. And there's a manual one, but you can just, you can do this manually or automated. Just click auto gain. And this works pretty well. So however you have the image oriented, if you have the GIF set up proper, it should transfer when you put it on to the GIF scan, okay? But you do have an option here, right? You can click rotate, and you do have the option here to adjust the rotation here as well, okay? I'm gonna put that back. If you right click, you can click on this guy, which is the park position, right? And if you click view, so now when you click view, that's where the beam goes. It's where it parks, okay? So we generally want this, away from the area that we're gonna be looking at, right? Now, unfortunately, with one of the things I don't like about this is there isn't like a crosshair here that I can, and that's a stage tool. There isn't a way to see. The only trick I know to do this is to put annotations on here. So if we come on right here, line annotation, let's see if it'll let me do this. Okay, so that's how we can find the center. You just draw a crisscross from left to right. Okay, so we're gonna put that basically in the middle. Or actually, you know what? I lied again. We're gonna go over vacuum here initially, okay? For what we need to do. And we're gonna park the beam right here in the center. And then we're gonna stop. So we have the beam and vacuum, okay? So now we need to, I'm gonna close this guy. Cancel. If you hold down Alt, when you close this, it should, not prompt you to save it. All right, so we have to decide here what we're going to do as far as our dispersion. So we have 3,000 channels here for our spectrometer. Okay, so if we do 0.75 EV per channel, it's going to give us a 1500 electron volt energy window. That should be enough for the energy or the core loss edges that we need to look at. Okay, if we did 1.5, that would be 3,000. That's a little bit overkill for what we need to do. So this was already on 0.75, so that's going to be enough. Obviously, if we went down to 0.3, that would be 900 electron volts. So you can see, right, Now this is higher dispersion as the number per channel gets smaller, okay? All right, so we can go ahead and focus the spectrometer here. So if we come here to the EELS palette, we want to make sure we're on HQ mode. Our energy is at 0. We want to start with the shortest possible exposure. So if you just type in 0, it'll take you to 100 nanoseconds, okay? And then click view. Okay, and we can see the ZLP. And so we can increase this a few clicks. We can click ZLP lock, and then we can auto tune this. So if we, sorry, we right click, no, where is it? Sorry, tune GIF, and then just do autofocus. So it goes through an automated routine where it tries to minimize the full width half max of the peak. We can, of course, take a look at the peak in 2 dimensions, and if necessary, we can do some, tweaking ourselves if we're so inclined. This is not like super high precision work that we're doing here. We're just, we're doing elemental mapping, so. And we're done. Okay, no improvement made. All right, so if we want to look at this manually, you can click here and click user tune. And we switch here to user. Okay, yeah, so this is basically perfect here. We're seeing it nice and, thin in the energy direction. It's not like twisted or distorted. Again, the user tune variables are here. This is the energy shift, but if we have ZLP lock, that should be taken care of. There's probably a little bit of improvement we can do with this though. So if we click FX here, you can watch what happens. Okay, so that spreads it along the energy axis. So we make this, as skinny as possible. Yeah, so we actually probably improve that a little bit more over the auto tuning. And we can go to FY. So this actually twists it about the center. So that looks pretty good right there. And then these other ones kind of change like some additional shape of the ZLP, but I mean this looks really good here, so I'm not even gonna mess with it. Okay. So actually, if we want to, we click on this and do 0 loss. Okay, so it's measuring actually higher than, well, we didn't change the exposure. That's probably why. So, okay, no, that's fine. We can leave that on. Actually, we can turn that off here. Do Control L. Control L auto arranges the windows. It's actually a pretty nice feature. So now I mentioned previously about checking that D scan. So I want you to watch what happens here as I move the beam around. Right, see the ZLP isn't shifting. Okay, and that's because we have the D scan activated. Okay, or we also have the ZLP lock on. Let me turn off the lock. Okay, you can still see even with the lock off. Now I get down here, I get into the PT, so I start to see more than a ZLP. Okay, but you can see it's not moving around. That's because we have D scan on. Okay, So I'm going to go ahead and turn on ZLP lock. Okay, and now if you have the ability to do dual eels, you always want to do dual eels, okay? So let's stop this. We'll click dual. Okay, and so for our low energy, that would be the ZLP. So we want this centered at 0. We'll leave it at what we had before. And then for the high energy, let's click silicon L99. And let's click view. Okay, so we still don't have this off of the spectrometer. So we need to move this off here. Okay, we should have enough of an energy because we're gonna ultimately we have to use, do background here to, when we do the silicon L23, which is going to be around here. So this should be enough. And of course, like our germanium edge is the highest edge, is going to be around here. So we should have enough here to do this. So, all right, so let's go ahead and start the scan. Okay. Now we have to adjust the exposure time so that we see what we need to see in the image, okay? Or sorry, in the spectrum, okay? So what we can't do, adjusting the focus here. Okay. So I'm going to switch this to preview mode. And we'll switch the high loss here. Yep, so there's the silicon edge. I can see it. There's the silicon edge. So we're trying to avoid this obviously turning red. And we're not really doing that yet, so we're okay. Yep, there's silicon. Curious if we can see the germanium out here as it goes around. Yeah, so we're really not seeing the germanium here, so need to increase this a little more. Okay, so now we're getting a little too high, so. All right, now we can try to shift a little more off of this. So if we bring this down a little more. Yeah, so there's the silicon peak. That's 1 millisecond, so we'll see what we get here. Yep, that's the carbon edge. And there's the silicon edge. And then the question is, can we see the germanium edge out there as it goes through? And I'm not sure if we're going to be able to or not. Part of it might be that it's just scanning too fast. So when we actually do the, the exposure, it might be fine. So All right, so anyways, what we can talk about now is, approaches to this. So again, we can do like a single pass here. You can see that this is still drifting upwards, right? So really we probably want to wait a little bit to see if this, might settle down. We can bump up the exposure time here for the ZLP. All right, let me switch this to search mode. Okay, I'm going to make use of my piezo stage, piezo move Y. Right, so we got a little bit of astigmatism here. So, I mean, we can try to, since we have a little time here, we can try to correct this. It's a little better. Okay, that looks a little better. All right, so right about there. Let's switch to preview mode. Yeah, so with a 1 second or 1 millisecond exposure time, it's going to be hard to drift correct here. Let's turn on 2D array. We're just going to do one pass. If we open up this little cog here, we click on eels, so we can use the pixel time as the total integration time, or we can just click auto determine based on what we have down here, which is easier, right? So you can click that. Okay, so that's going to keep the pixel time the same. So why don't we actually, let's just use SI pixel time, and then put this at 1 millisecond. Okay, so we're just going to do one frame. And we'll see here, it's going to take 46 seconds. All right, so it's not drifting terribly here. All right, so then we have to figure out the step size. Now, if we want something comparable to the image, do Control D, image info. All right, so our pixel size right now is 0.5 angstroms. Okay, so if we want something similar, we can do that, and then we can lock it in place. So now this has the same resolution that the image has roughly. So that's 0.5. Why don't we unlock this? Let's just put it at 1. Whoops, 1 angstrom. Okay. Nope, sorry. Okay, 1 angstrom. Lock in place. There we go. Okay, and then there's other options in here. So you can tell it to blank the beam afterwards, which is a good idea, right? So you're not, pasting the sample. So it's going to take 40 seconds here to collect the spectrum. So let me move the park position out here. And so obviously, if we're just doing one frame, we can't really drift correct. But let's do one frame, and let's see what we get here. And so just to make this kind of more aesthetic, let's do 56 by 128. Okay. All right, so we're going to do that. All right, and then we'll click. We don't have to let this stop. We can just click capture right now. There's the carbon edge right there. There's the silicon edge starting to come through. Okay, then we're into the germanium, silicon germanium, I'm sorry. And then we're back into the silicon. Okay. It's applying dark correction. And we'll just click OK. All right, so it's asking about don't worry about saving this for right now. All right, so hold down Control, left click and drag, and we get the picker here to see what we've got. Okay, so let's turn off the low loss and just look at the high loss. So there's our silicon, right? Actually, okay, there's the carbon edge right there. So right here, there is the oxygen K. Yep, there's the oxygen K. And there's a little bit of there's silicon, right? Because it's silicon dioxide, presumably. And then we see the silicon, and now do we see the germanium? It's going to be out here, so it's going to be much weaker, but do we see it? Yes, we do. There's the germanium L23, it's right there. So we got it. And then we get back to the silicon K. All right, perfect. So we have to mark the edges now that we want to map, okay? So let's start, we'll go top to bottom here, okay? Let me pull this back. Okay, so on the spectrum here, you can right click where you see the edge, add to quant. There's the carbon K. Move this down into the oxide. Right click here, add to quant, oxygen K. Okay, move this back over here. Hopefully we have enough silicon L, sorry. And then in here, this is the germanium. Again, make this bigger to make it a little easier to see. Germanium L, perfect. All right, so now from here, go to the elemental quantification palette, and we can check a few things here. So we can open up the analysis. We don't really have a problem with any peak overlaps in this situation, which is really nice. If we thought we were seeing that, we could, say, well, this overlaps with, it really doesn't though. It's separated by a lot here. See, this is the carbon K. We expand this box. Yeah, to include the silicon. So it really doesn't, it really doesn't overlap the L much. And then the same thing, we really don't see an issue here with the oxygen overlapping with the carbon signal either, carbon peak either. So, I mean, if there was an overlap issue, we could do that here, and this handles it pretty well. Assuming the overlap is not like terrible. Okay. Now the other thing with this too, the defaults with this are pretty good, but you do have the option here to specify the integration window. So you can see right now with the oxygen, it's including the energy loss near edge structure. Now there's a lot of signal in here. So if you wanted to include that, you could do that here. And that will, improve the signal window that's integrated over. From a quantitative standpoint, it's not ideal because it's harder to model this from a cross-section standpoint, but from a signal integration standpoint, it's obviously much better. Okay, so you can see, right? I mean, this is modeled much better when we exclude the LNES. Again, so if we're trying to get quantitative information, we want to do that. If we just want to, map signal, then we can exclude that. Okay. Let's go to the silicon L. Okay, and then, same thing, we can exclude that. And again, it's going to integrate over this window. So then we have the germanium. No, I mean, there shouldn't be a huge difference with these. So here, why don't we actually can exclude the L-ness. We'll just leave the defaults here. Just wanted you to appreciate what's happening here when this is occurring, okay? All right, so we're good to go there. You can manually adjust these here if you want, right? Your windows. So like in the case of the silicon, probably makes a lot of sense to make this a little bit smaller because we're getting kind of close to the, plasmon peaks here. So you can manually do that. If you mess this up, just click this, it'll put it back, okay? So let's leave that there for the silicon. And then we can click map. So let's display on the same workspace. Let's go ahead and add maps. And we'll just do a signal. Well, qualitatively, these are going to look the same anyway, so it doesn't really matter. But we'll just do signal integral. If we do scale by cross section, it's going to do signal integral divided by the calculated inelastic cross section. So, all right, let's see what we get here. Someone's calling me. Oh, sorry, let me get this for a second. Oh, I can in like a few minutes. I don't know if you can wait that long. If you can, I understand. Certainly. Okay. Okay. No, I'll try to be there in 10 minutes. Okay. Okay. Thank you. All right. Sorry about that. All right. So here we go. So we have exactly what we would hope to see here. Let me minimize this and this. And we can do Control L. And so we can actually see the silicon, and we can see like atomic level detail actually in the silicon, which is pretty neat. We can color mix these. So we click add. Whoops, not ADF. And there we go. So yeah, we see exactly what we would expect to see. So there's our oxide, there's our carbon layer, silicon, germanium. I don't know what the composition of this layer here is specifically. It's actually fairly diluted germanium, but we were able to, detect it with the eels, of course, and then the silicon underneath it. And then if you click SRC right here, it recolorizes all of these. So, we can kind of play around with some different color schemes here. I mean, red, green, blue, those are your probably you want those to be your three main colors. I mean, if you want to try the germanium with this cyan color, yeah, so it automatically updates it. Or we can try the magenta, which should be that guy. Yeah, that's a little bit better, I think. And then your next three colors usually cyan, yellow, and magenta. So the system will usually, automatically do those for you. Let's try instead making it red. And let's make the carbon yellow. Not very good, I think. Yeah, and I'm actually not sure at the moment. I think this is the magenta here. No, actually, oh, I think it's this one actually. Let me check here. We can find out pretty quick. Yes, so this is the actual magenta. Yeah, I can tell based on the color wheel here. So, okay, no, that's fine. All right, so there you go. If we want to add a scale bar here, you can do layout, add scale bar, and there you go. So, I mean, you know, this is close to atomic resolution that we're getting here. I mean, we can actually see in the silicon, right? That this is, we used a 1 angstrom step size, but you can see that this is atomically resolved. So, or close to atomically resolved. So very neat. So we have a finally successful, and then you do Control L, it auto arranges your windows. So we finally have a successful EELS experiment here. Now, of course, we could have done multiple passes. The problem with that is you need this, the sample has to be really still for that. Okay, so based on how short or how long it's taking per frame, right? It's taking about half a minute per pass right now. And that's a little bit of a problem, okay, in terms of being able to accurately drift correct. So the sample has to be, you know, stabler than it is right now, okay? More stable, I should say, than it is right now in order for this to work, okay? If it was stabler, we could have, more stable, sorry. We could have done multiple passes and enabled drift correction, but you know, in this case, we had to kind of take the single pass approach, and it still obviously produced a useful result, okay? So we were able to see what we what we were expecting to see, okay? All right. So at long last, that is the crash course on doing the STEM-EELS. So if you have any questions or comments about that, of course, please feel free to let me know, okay? And thanks again for all your support, and looking forward to doing more videos soon. All right, take care, everyone.